Welcome to the course on principles of vibration control, and today we are in the 10th lecture, in which we will be continuing on our discussion on linear viscoelastic materials and its models. So basically we will talk about how we can develop mechanical models of viscoelastic materials. In this direction I have already told about Kelvin-White model, how you can keep a spring and a dashpot in parallel to develop a Kelvin-White model. Today we will show how you can develop a Maxwell model, and then extending that further, how you can develop 3-parameter models like standard linear solid and standard linear fluid models. So SLS is our standard linear solid short form, and SLF is standard linear fluid. So we will see how we can make all these models by following very similar principles. So first let us concentrate on the Maxwell model. Now in the Maxwell model we have the spring and the dashpot. These two are in series with each other. So let us imagine that we have applied a force which is causing a stress sigma and the overall strain epsilon, okay, in the spring dashpot model. So suppose if I fix it in one side, apply a force, then the stress is sigma and the strain is epsilon. Now this there are two things we need to think of it. One is that since there is no other connectivity from input to the output, so the same stress will be there in both the elements, both in spring as well as in the damper. So that is what is our second equation says, that this sigma is the same as sigma 1 and it is the same as sigma 2. The other thing is that about the strain, it is just the reverse of Kelvin-White model. In this case the total strain epsilon is actually the strain that is shown by the spring and the strain that is shown by the damper, which is epsilon 2. So our epsilon, the total strain that is given by the first equation, is actually epsilon 1 plus epsilon 2. Now if I take the derivative of the first equation, then the rate of strain is actually d epsilon 1 dt, that is the rate of strain in the spring element, and d epsilon 2 dt, that is the rate of strain in the damper element. Each one of them of course we can very easily find out, because we know that sigma equals to E epsilon, which means sigma 1 equals to E epsilon 1. So d sigma 1 dt is E d epsilon 1 dt. So that is something that we know, and the other one d epsilon 2 dt, for that we can use this model, and from which we can say basically that d epsilon 2 dt is nothing but sigma 2 over eta. So then we can actually write this equation 3 by substituting all these things in the right hand side, that d epsilon dt is actually d epsilon 1 dt, and that is written in terms of from this one a little bit of simplification, that d epsilon 1 dt is 1 over E d sigma 1 dt. So that is our first part, and the second part is d epsilon 2 dt, that we are taking for the viscoelastic material from this relationship, that d epsilon 2 dt is nothing but sigma 2 over eta. Now since your sigma is nothing but sigma 1 and sigma 2, the same stress is flowing through the entire system. So the stress is not changing, hence you can, instead of sigma 1 sigma 2, you can denote them as sigma here itself. So you get the final relationship very straightforward, that d epsilon dt is 1 over E d sigma dt plus sigma over eta. I already told you that the fundamental definition of generalized. So, this is the generalized Hooke's law. Okay. So, this is the generalized Hooke's law, and in that if I try to fit this model, then naturally our A 0 sigma, that A 0 will be 1 over eta, that is this term, and then our A 1 d sigma dt, only up to first derivative we can go. A 1 will be nothing but this 1 over E. So, that is what is 1 over E, and in the right hand side B 0, there is no constant term there. So, that means B 0 is 0, and B 1 is actually unity. So, B 1 is 1 here. So, thus this generalized Hooke's law in this format, if I have to write, then I have to write it in a manner that this equation will simply become 1 over eta sigma plus 1 over E sigma dot, and that equals to, where the sigma dot means d sigma dt, and that equals to 0 times epsilon, because the first one is constant, plus 1 times epsilon dot. That is what will be the relationship in the form of generalized Hooke's model, if you apply all these parameters. So, this is what is our Maxwell mechanical model. Next, let us try to look into it, that okay, we have proposed a model, how this model is going to behave with respect to two things. One is the creep recovery and another is the stress relaxation. Now, when we will talk about creep recovery, you have to keep in mind that we are going to apply the force only once and then we will keep it steady. That means, it will behave like a Heaviside function. So, if I try to plot the T versus the load F, suppose I fix this side and I apply the force F, then the force F will be of this type in nature. That means, it is like a step function. Okay. So, some force F 0 and then it will remain constant. So, our Maxwell model equation is this, which we have already declared, and we are applying some force. If we apply the force, what we will see is that the spring is going to deform instantly. So, there will be some strain in the initial strain in the system, which can be denoted as sigma 0 over E. Now, that is my initial condition, and then you will see that the stress is not changing anymore. So, there is no further stress rate that will come into the picture, which means this part will not be coming into the picture. So, you can write epsilon dot equals to then the whatever is the initial stress sigma 0 over eta, and then you can integrate this equation in terms of sigma 0 over eta t plus c, that is the integration constant, and apply that at t equals to 0, your epsilon 0 is sigma 0 over E. So, you apply that condition, then your C will be sigma 0 over E. That means, your epsilon t will be sigma 0 over eta t plus sigma 0 over E. So, if I have to plot that with respect to time, it will be something like sigma 0 over E as the initial value, let us say somewhere here in the same plot, and then it is going to be a constant a uniform slope, okay, constant slope line, and the slope is sigma 0 over eta, that is the slope of the line. With that it will continue. So, this is the solution that Maxwell model is going to tell us. In fact, you can write it in terms of a creep compliance function such that this J t. So, if you write a sigma 0 in one part and the rest the time varying part, then the J t time varying part, the creep compliance function will take the shape of t over eta plus 1 by E, showing thereby that it has a linear creep compliance function is linear in nature with respect to time. So, this is the relationship for us, and this is the J t that we have discussed. Now, what will happen if the load is removed? then the spring will react immediately, but the dashpot will have no chance, no tendency to recover. That means, this is epsilon and time plot. So, you have the initial strain sigma 0 over E, and then as I told you that it will increase. After some point, if you immediately release the load, that part will be recovered. So, that is the recovery part of it, sigma 0 over E, and then it will continue, the plastic strain will continue. So, there is an immediate elastic recovery that will happen with the creep strain remaining due to the dashpot. There will be no anelastic recovery in this system, but there is only elastic response and a permanent strain. Now, this Maxwell model therefore postulates the creep or constant stress condition that strain will increase linearly with time. However, polymers for the most part show the strain rate to be decreasing with time. So, as a result, this does not match with our usual type of response that we find in the polymers. So, Maxwell model is actually unfit as far as the creep response is considered. How about the relaxation response? So, if you look at the this is the creep recovery part of it, but if you look at the relaxation part, maybe I will just talk about the stress relaxation first, and then there what we are giving is that we are subjecting it to a constant strain epsilon 0 at t equals to 0, and then we are actually measuring that how the stress is changing. That means, with respect to time, if I plot now not the stress, but the strain. So, you are giving epsilon 0 and you are holding it, and you are trying to measure that what is the change of stress in the system. Now, we already know from the model that sigma t is epsilon 0 E t, where E t is e raised to the power minus t by t r, and this t r is actually eta over E, and analogous to the creep function j, our function here is the relaxation function E t, the relaxation modulus function, and this time t r is very critical. The t r is called the relaxation time of the material, which is a measure of the time taken for the stress to relax and to come down to 0. So, what we expect is that at t equals to 0, we expect that this E would be e to the power this thing will be 0. So, e to the power 0 will be unity. So, you will get a constant and you will get the epsilon 0. So, that means you will get some constant value, and then so if I try to plot the stress, so it will be something like sigma 0 and then it will be constantly coming down. So, that is what will be the nature, exponentially it will come down. So, thus Maxwell model predicts that stress decays exponentially with time, and that is found accurate to be most of the polymers. So, the limitation of Maxwell model is that it does not predict creep accurately, but it does predict relaxation accurately, and this is observed in thermoplastic polymers in the vicinity of their melting temperature, fresh concrete, if you neglect the aging, or numerous metals at a temperature close to their melting point, you will observe this type of a nature of stress relaxation. So, the Maxwell model can be applied in such a case. Now, this relaxation time T r, that can be actually further used in terms of a number that is called Deborah number. So, it is a dimensionless number and it is used to characterize the fluidity of materials under specific flow conditions, and it is based on the premise that given enough time, every solid will behave like a flow like manner, and this number is defined as the ratio of T r over T p, where T r is the relaxation time of that particular material and T p is the time scale of observation. That is important, that suppose you find something is very much solid like. So, that means its Deborah number is actually very high, and if you see that it is behaving like a flow, that means the Deborah number is actually quite low. So, the Deborah number will be low, which will signify if there is a low Deborah number, that may signify that for the same relaxation time your time of observation is quite high. Let us say instead of measuring in terms of seconds, you are measuring in terms of months or years or thousands of years, so then you will see the flow like behavior. So, this is another interpretation of the Deborah number. Now, with this basic mechanical model, we will actually go to slightly higher order model, which is known as a 3-parameter model, and you would see that the limitation of Kelvin-Voigt model, that it does not describe stress relaxation, and the Maxwell model, that it does not describe creep recovery. This can be actually answered with the help of this higher parameter model, which are used to predict both the phenomena. So, we will try to find out the formulations of some of these models now. As 2-parameter models cannot explain creep and relaxation appropriately, so we are going for higher order models, and hence we will discuss about two different types of models. One is 3-parameter models and another is a 4-parameter model. You can even go for even higher order models, but at least this will be good enough for most of the observations. Now, in the 3-parameter models, we will have two variations of it. One is called Zener model and another is called anti-Zener model. Zener model would look something like this. There are two types of Zener models. One would look symbolically as three elements we have to have, right. So, we have a spring and we have a damper followed by a spring. So, this is one variation of a Zener model. The other variation of a Zener model is something like this, that we have two branches to begin with, one spring, one damper. So, one branch is like the Maxwell model, which we have just now discussed, and together it is like a Kelvin-Voigt model, and it is coming out as the output. So, one of the Zener model is like Kelvin-Voigt and then another spring in series, and here it is Maxwell and another spring in parallel. So, these are the two Zener models. And then we will look into the anti-Zener models. This also will have two variations in it. One variation is that these variations are in terms of the damper now. So, here in these 3-parameter models we have used one damper in both the cases and two springs. In both the cases. However, in this model, anti-Zener models, we will use two dampers and one spring, just the reverse. That is why it is anti-Zener model. So, you can see that there are two dampers and one spring. Naturally, there is one more variation possible of it, and that variation would look something like this. So, here also you have 2 dampers and you have 1 spring. So, these are Zener and anti-Zener model. If I go for 4 parameter models, then the model that generally is used is called Burger model. And there are 2 variations of the Burger model here, a spring and a dashpot together, that is the Maxwell element, and then we are branching out and we are going to have 1 damper and 1 spring together, then we are coming out. So, that means we have a KV, we have a Maxwell, we are joining them together to get the first Burger model B1. The second Burger model would look like that, means you have 2 Maxwell models in parallel, both are Maxwell here. You have 2 Maxwell models in parallel like as if a KV form. So, this is B2. Once again B1 model is used mostly for creep and B2 model is used mostly for relaxation. So, these are the 3 parameter and 4 parameter models. Now, if the parameter increases, how am I going to develop the generalized Hooke's law or the constitutive relationship? Let us look into one simple case which you can later on work for all other cases. So, let us try to work on one simple case which we will call as the standard linear solid model. Standard linear solid SLS. It is a form of a Zener model and this will be something like, let us try to draw it. So, we have 3 parameters here, 1 spring and then you have another spring and a damper together. So, this is the model. So, as you can see here that you have 2 springs and 1 damper, which means that it will behave like this, a Zener model which has 2 springs and 1 damper. So, this is the standard linear solid model, SLS model. And in this model, let us say the stress here, overall stress is sigma and epsilon as I am applying a force F, and let us say I am fixing it here, easier for us to visualize. The stress is going to be divided into 2 parts. One is this part, say here the stress is sigma 1, strain is epsilon 1, and here overall the stress is sigma 2 and epsilon 2, but it is divided into 2 parts here. So, in this case it is, let us call it sigma 2 1, epsilon 2 1, and let us call the stress here as sigma 2 2 and epsilon 2 2. So, thus we have defined all the basic parameters. So, let us quickly see what are the relationships that we can get from here. First of all is that this sigma is actually sigma 1 plus sigma 2. So, we can write it down that sigma, by studying this, sigma is sigma 1 plus sigma 2. And what is epsilon? Epsilon is actually the strain is same because it is a parallel model. So, it is epsilon 1 and that is epsilon 2, that is what is my second equation. Now, for the Maxwell arm, that means for this arm, let us try to close on it further. So, for the Maxwell arm, one is that epsilon the strain itself or epsilon 2, whatever you will call it, this is nothing but epsilon, we have already said, and that equals to epsilon 2 1 plus epsilon 2 2, because it is a Maxwell part of it. And we also can say, so let us put this as equation 3. We also can say that sigma 2 1 in this part, it is like a spring. So, it is E 2 epsilon 2 1. So, let us say that this one has a modulus of E 1, this one has this spring has a modulus equivalent of E 2, and this one has a damper equivalent of eta. So, ultimately we have to express everything in terms of E 1, E 2 and eta, because these are the 3 parameters. Okay? E 1, E 2 and eta. These are the 3 parameters that we have. So, ultimately you have to express. Okay. So, we have expressed sigma 2 1 as E 2 epsilon 2 1. So, let it be our equation number 4, and also we can write sigma 2 2, and sigma 2 2 is actually eta epsilon 2 2 dot, and that is our equation 5. So, we have all the basic equations with us, all the basic constitutive relationships with us. Regarding sigma 1 I did not write, but we can write that also, that sigma 1 is E 1 epsilon 1. So, let us try to now quickly see that how we can apply this whole thing. First of all, a Laplace transformation LT, okay, and you should be knowing that the Laplace transformation of Ft is denoted as f bar s, and also you should be knowing that if it is a Laplace transformation of f dot t, that is the derivative with respect to time, then you can write it as s f bar s minus f bar 0. So, in this case we will use the 0 initial condition. So, this will be 0 here, and so in this case if we convert these equations, for example 4 and 5, if we use the Laplace transformation, then we can write sigma 2 1 bar now, that equals to E 2 epsilon 2 1 bar, and sigma 2 2 bar equals to eta s epsilon 2 2 bar. That means, we have used that 0 initial condition here. So, sigma 2 2 is eta s epsilon 2 2 bar. So, we can use these two things together in our equation. So, we now know that epsilon 2 bar we can write now as, with the help of this we can write now that epsilon 2 bar, that is the overall epsilon strain. So, epsilon 2 bar is actually the Laplace transformation of epsilon 2 itself. So, epsilon 2 bar will be epsilon 2 1 bar plus epsilon 2 2 bar. So, it will be epsilon 2 1 bar plus epsilon 2 2 bar, and by using these two equations we can write that epsilon 2 1 bar is sigma 2 1 bar over E 2 plus sigma 2 2 bar over this epsilon 2 2 bar. So, it is eta s. So, that is what is our epsilon 2 bar. In fact, I can also write it as little bit cleanly 1 over E 2 plus 1 over s eta times sigma 2 bar. Of course, we have to keep in our mind that sigma 2 bar and sigma 1 bar. So, this summation is actually sigma bar. So, we have to use this at the second stage now. So, we can write here from this we can simply write that using this relationship sigma 2 bar is actually 1 over this 1 over E2. So, maybe we can actually write it in one shot, you can do the algebra on your own. So, we can simply reciprocal we can take and write it as S eta E2 over E2 plus S eta, just carrying out this whole thing directly times epsilon 2 bar. So, this is what is our first part of the thing. We can also see here that for this entire part epsilon 2 bar is epsilon 2 and epsilon 2 is epsilon 1 and that is epsilon. So, we may also write that this sigma 2 bar is actually S eta E2 over E2 plus S eta epsilon bar, because the strain is the same. So, we can use that, and let us now use the last equation, that is sigma equals to sigma 1 plus sigma 2. So, I am just erasing this part now, the middle part, because these things we have already obtained. So, our one relationships we know is this relationship, that is what is sigma 2 bar, and now we know that sigma bar is sigma 1 bar plus sigma 2 bar. Okay, that is the Laplace transformation of the first equation. So, from this first equation we get this. So, we can write sigma bar as, what is our sigma 1 bar? Now, sigma 1 is simply E1 epsilon 1, it is a simple spring element. So, actually it is sigma 1 bar can be written as E1 epsilon 1 bar, and sigma 2 bar can be written as S eta E2 over E2 plus S eta epsilon bar. In fact, epsilon 1 bar is nothing but epsilon bar. So, I can even remove this one now. So, we are very close now, the constitutive relationship is already there, but it is in the frequency domain. So, we can convert it to time domain now, and if I convert it to time domain, so use inverse Laplace transformation, then this should become, we have sigma plus eta over E2. So, you can carry out this on your own, sigma dot, and this will become E1 epsilon plus eta E1 plus E2 over E2 epsilon dot. So, remember our generic Hooke's law was something like A0. So, A0 is actually unity here, and A1 is actually eta over E2, and B0 is E1 and B2 is eta E1 plus E2, eta E1 plus E2 over E2. So, we can very nicely fit the whole thing in terms of the generalized Hooke's law. So, just the same way. So, that means in this case all you have to know is this E1, is this E2 and is this eta. So, similarly for the other model also you can do the same thing, and you can find it out just by using this technique E1, E2 and eta, and also you can carry it out for all other anti-Zener models and 4 parameters models. I have just shown how to do it for the one of the Zener models, that is the standard linear solid model. So, let us summarize the whole thing now. We will now summarize all our observations in the following slides. that this is the standard linear solid model which we have just now derived and compare it with the Hooke's law. So, this is one model, and then this is the standard linear fluid model, that is where you have 2 damper and 1 spring. So, that is something like one of the anti-Zener models, and in this case the relationships you can derive, this is the way it will come out, and you can fit it with the generalized Hooke's law with these values. You have to keep in mind that all the higher order values A2, A3s, these are all zeros, and similarly B2, B3s, all higher order terms are zeros, that is for standard linear fluid model. And further also, so our complete summary is that we have discussed about 1 parameter models, we have discussed about 2 parameter models, Kelvin-White model and Maxwell models. So, the linear elastic one was perfectly elastic, linear viscous was perfectly viscous fluid, Kelvin-White model predicts solid like behavior, some amount of viscosity is there, do not describe stress relaxation, and Maxwell model predicts fluid like behavior, do not describe the recovery. In order to do that, we have actually worked for higher order models. These are the 3 parameter models, some of them like the standard linear solid model and standard linear fluid model. And even if we get a nature which is not satisfied by these things, then we go for Burgard's model, which we have described, and these are the relationships of the various parameters in these models. So, with this hopefully you will be able to model viscoelastic materials properly with the help of any of these material models. So, this is where we will come to an end. In the next lecture, we will talk about complex elastic modulus viscoelastic material, frequency and temperature dependence of viscoelastic material, and application of viscoelastic laminae. Thank you.